we just have one piece left, the adaptation part for this big structure of Adaptive Disturbance Observer. Here is what we have now. We have the baseline. We have a baseline feedback loop. And then we have this so-called disturbance observer structure in this dashed box, where we have utilized a nominal inverse of the plant, which is essentially, if we know BA, I would do nominal all right, so a nominal version of the inverse of the plant without the delay terms, and delays are separated into here. Effectively, we generate an estimated and delayed version of the disturbance with some noise. And we know from our analysis that the way that we design this Q to integrate this internal model A inside is as follows. So the overall, the starting point of the internal model design is we have this polynomial that will filter out the disturbance and then generate a zero. So we design this way to, in the end, have a magnitude response of this filter, 1 minus d negative mq, to have this notch shape. That's a known fact. And then we also know that for one band, we have this polynomial A will have this shape. All right. It is a nonlinear. It is still a nonlinear function with respect to omega, the disturbance frequency, but it is linear if we define this new parameter A1 to be equal to this -2 cosine omega 0. So by a transfer of variable, we can have a linear internal model designed in our controller. And for the case when we have two bands, we have this mirror symmetric model. So it is not difficult from here to write out the denominator part of the design over here. It is going to be alpha A1 for the one band case, and then 1 plus alpha A1 Q inverse alpha square A2 Q negative 2, and then alpha to the power 3. Okay, so from here, be a little careful. A has this mirror symmetric structure, but A alpha Q inverse no longer has this mirror symmetric structure if n is larger than 2, if you have 2 or more disturbance frequencies, because of the alpha is going to be scaled as your order of Q increases. All right, so be careful, do the programming here. Now, let's finish up this frequency domain analysis a little bit more. If I know we have analyzed the magnitude response to look like this, let's take a look at the magnitude response of this Q now. So the magnitude response, to be more specific, it is 1. It is close to 1 at both the low frequency and high frequency. And then at the target frequency, let's say one band, is going to be 0. So we can do the analysis over here again. If this entire term is 1 at low frequency, so that means this part at low frequency, the magnitude should be approximately 0, right? So I know the magnitude response of this filter should be, because of this design over here, it should be pretty small at low frequencies. It is also pretty small at high frequencies. So these 2 points now should be giving us these, correspond to these 2 points here. And then when it is 0 here, then 1 minus 1 is 0. So at this target frequency, it is 1. So the shape will roughly look like this. Now, this is very close to the picture here now. We do this because we wanted to understand how intuitively this Q filter will process my disturbance estimate over here. And from here, we can see that it is going to act as some kind of bandpass effect. First of all, it's going to filter out the noises at other frequencies, especially low and high frequencies. So this has a bandpass effect. And then second is what we talked about, this shift of delay operation, and act to provide phase shift. And more specifically, it is actually phase advance. All right, so you have a delay in the signal here. It is actually going to be advancing the signal phase to make it to be correctly stamped at time k, counteract the delay effect. Actually, it's m-step delay. Okay, so there are 2 components here. This part is easy to recognize, and it has been the practice in the past. But this part is not as trivial to understand. Okay? So now we have the complete picture of both the block diagram domain and then the algorithmic domain. Let's now talk about the adaptive control part. The adaptive control part is starting from here effectively. So we know in the perfect scenario, in the deterministic case, if we know the disturbance frequencies, we have this, right? So we have our design of Q will give us this extended internal model principle. All right, so we know our design of Q will contain this term, and therefore it's going to converge to 0 gradually if all the parameters are known. These are the extended terms that we discussed in the last lecture. All right, so in the simple case, for the case when m equal to 1, then this is just 1. All right, so only when you have more delays, then this term gets more advanced. So we know this picture now, regardless of what kind of m is in the plant delays. And if we write it out, it's going to be, for example, if we just have one band, all right, so for this case, let's work on this a little bit more. We have A alpha So dk. We have this. If we define this signal as, let's define it as ek. The deterministic case, should give us 0. All right. So therefore, we can design. We're going to do two things. We're going to design a recursive least square series parallel adaptive control. And then a parallel adaptive control algorithm with a fixed compensator. Let's do this part first. Okay, so ideally ek is 0. All right. So in the adaptive version, we are going to adapt A we let A1, this is the only variable. We're going to change it to an adaptive version and compare the ideal output with our estimated output. Let's say E hat. Okay, so we're going to design let's do this. So let's transform the Planck model into our regressor structure first. All right, so Planck model transformation. This one, treat this as the input, treat this as the output. So ek is going to be multiply the denominator to the left. We're going to have ek plus alpha a1 ek minus 1 plus alpha square ek minus 2 equals dk plus a1 dk minus 1 plus dk minus 2. That's the model here. And it is equivalent to, therefore, by changing terms a little bit, we are going to have this term contains a1, this term contains a1. So it's a1 minus alpha a1. Actually, it's a1 times dk minus 1 minus alpha ek minus 1. This is the unknown parameter and the coefficients. And then plus dk minus 2 minus alpha square ek minus 2. All right, so this would be phi. This is our theta. This is phi k minus 1. All right, so in the scalar case, we don't need transpose. I'm just going to write it this way. So for recursive least squares, we're going to replace design. Let's do the a posteriori version. All right, a posteriori estimate is going to be theta hat k phi k minus 1 plus, let's just leave it, plus dk minus 2 minus alpha square ek minus 2. This is the a posteriori estimate. And then the a priori estimate is theta hat k minus 1 phi k minus 1 plus d k minus 2 minus alpha square e k minus 2. All right? And then this is the estimate. All right? The adaptation error is the difference between your estimate and your assumed plant output. All right? So it's going to be in our notation in the class, the way we define the error is the actual minus the estimated. So the signs actually matter over here. It is going to be, let's call the adaptation error to be epsilon. Right? The a posteriori is going to be ek minus e hat k. And the a priori is going to be this. And then the adaptation PAA is going to be, the recursive least squares is going to be theta plus 1 plus f so it's the usual form. All right, so that's the PAA. Just using the notations defined over here. You can do the adaptation gain. This is updated in exactly the same form. So use the same adaptation gain evolution. If you want to include some forgetting factor, let's do all right? So in this case, all these are scalars, so it's actually very easy. You don't need to even write the transpose sign. Now, these are all standard out of the formulas in the class. Let's adapt this. Let's think about the problem a little bit more. This is actually can be further simplified. The observation is as follows. First of all, the ideal output is 0. All right, if I know the parameters is 0. So this is actually just an E negative E hat k. That's the first simplification. Now second, if this is 0 for Ek, all right, then these guys, Ek minus 1, Ek minus 2, in the ideal case, they are also zeros, right? So therefore, this phi vector is also simplified. So using a different color, we can get for RLS, because of this, we're going to get this is going to be 0, and this is also going to be 0. And same thing here and here. So a lot of actually beneficial cancellations, beneficial reductions of the complexity. All right, so that is the recursive least squares update. All right, so this is not going to be perfect when you have noises, as we know. Recursive least squares has great stability, so the conditions are always stable. All right, that's the benefit for this. But the convergence is not as good. If we want to get more accurate, the way to do is actually to use some kind of replace series parallel with some parallel structures. And we will do this parallel with a fixed compensator design. So the way to design a parallel structure, as you would recall, is something like this. We have an unknown model, and we update with a parallel PAA like this, right? So that's how we do the parallel PAA. Let's call this case here. So EK is going to be say this is DK. It's going to be this, and when we have just one band, let's write this out this time. There's some subtle difference, as you will recognize immediately. So replace all the unknown parameters with their estimate. We have this is our relationship between D and E. So in other words, we can write it again in a form like this. It's going to be EK plus alpha A1 hat EK minus 1. On the left side, you no longer have this A1, but you have A1 hat in here, plus DK A1 hat K and then plus DK minus 2 here. So your regressor is actually different now. It's neg. I'm going to combine this. I'm going to do it in one step this time. A1K, DK minus 1 minus alpha EK minus 1. All right. This time, this signal is not always 0 because this is the disturbance filtering through this adaptive output, adaptive transfer operator. So this is not always 0. That's the difference. So therefore, let's call this phi again, K minus 1. And this is our theta hat. Okay. We have PAA. Let's do the adaptation error first. Epsilon, let's do the A posteriori and A priori. It's going to be, this is the epsilon. All right, so it is the difference between this and this. This is the ideal plant. This is the estimated adaptive version. This line, ideal version, it is still 0 here. So it is negative EK and theta phi k minus 1. Okay, and then this is the a priori. It is just to replace this with k minus 1. So that's the adaptation arrow. And you can do now PAA again, PAA formula. Actually, this is we haven't talked about the fixed compensator part. So this is the pure direct output of the adaptive version of the system. And then for fixed compensator, we actually define a filtered output. Let's call it this. So filtered output is this adaptation, this direct arrow between our true and estimated output going through a fixed compensator. Let's call, ideally the fixed compensator should be 1 plus C1 all right, so it resembles the structure of, ideally this is 1 plus A1 Q inverse plus Q negative 2. So ideally it should resemble the true Blount numerator, but we don't know at the beginning. So this is C1 should be ideally A1. And in reality, we can do an estimate. We can try our best to find what might be possibly physically. All right. If we don't know absolutely anything about A1 in practice, we don't know anything about the disturbance frequency, omega, then what we can do is can be initialized with recursive least squares. All right. So in reality, the two will be combined together. We first run a recursive least squares PAA. We get a rough, not so accurate version of A1. And then we improve it with a parallel PAA by assigning the initial, possibly not accurate A1 into the compensator. So that is the basic idea of the PAA, parallel PAA. All right, so the exact formula will look like this. Nu k is going to be epsilon k plus C1 epsilon k minus 1 epsilon k minus 2. And a priori version is going to be this. Okay, so a priori version is going to use whatever that's possible at time k. At time k, the only possible actual implementable version is epsilon naught k, the a priori version of epsilon. And then these two are available, so they are implemented in here. And the PAA is final PAA is epsilon theta hat. Okay. Phi. And then the usual. All right. So this version that I put here is slightly more detailed than the version used in the paper. This version has included all the signals, all right, in its explicit form. You can compare and digest a little bit more after class. Now, let's talk about one thing. We said we need to initialize. This covers everything once your algorithm has been running. We need to initialize it a little bit somehow. So for recursive least squares, usually it's pretty tolerable. The algorithm will always be stable, so it may not converge 100% to the absolute value, but it's going to be able to be reasonable with, even if you try initialize it with 0 in recursive least squares. All right? But what will usually be more beneficial in practice is to respect the physics. So from the physics aspect, we know that theta is parameter A in here. And for those who noticed what I wrote, A is negative 2 cosine omega 0. All right? So from the physics aspect, we need to, the way to do is to leverage as much information as we know about the disturbance. If I see the structure here, then what can be done is, let's say, we have some estimate of this, all right? Even if it's, let's say, initialize it with best possible guess. Even if it's 0, it's going to be better than this one, actually, you will see. Right? Even if you initialize with, you say, I absolutely know nothing, so let's try and assign this to be 0. Then it's going to be negative 2 times 1. All right? So this subtle difference in how you initialize the algorithm will actually create major differences in the algorithm convergence. You will commonly see that if this is 0, then it might either take longer to converge, or it may have large overshoots or undershoots in the evolution of theta signal. All right? So this is a case if you just have one band. And in the paper, I talked about the case if you have multiple bands. All right? The case over there is, again, to do your best guess based on the physical parameters, how they relate to the physical parameters. All right? This is everything for the adaptive control part. And these are just 2 examples, as Toby recognized. You can do other PAAs as seen possible. This is the version with the minimum amount of adaptive parameters. All right, I think that's everything for the algorithm.